Alright guys, we're back to talk about the squeeze theorem. So in calculus, one of the fun things you get to do is learn a lot of theorems and then use them as proofs in your answer so that you don't have to do all the work that the original mathematician did to prove the theorem. So I'm going to go over the basics of the squeeze theorem and how you use it to find the value of a limit. So we're going to assume you have two functions here. Here's function h of x, this pink one, and then here's function f of x, this purple one. I didn't draw the arrows on the end, but you get the idea. And then we're going to talk about the value or the limit of these functions at some point c. So this point right here, which I drew the line up. So we're going to pretend, as we're going to squeeze, I'm going to squeeze a function in between these two. So I'm just going to draw one. It doesn't really matter as long as it's in between these two at point c. Okay, so there's my function, my pencil function. You can see it goes right in there. I'll trace over it in a different color so you can see it better. But let's imagine this is the function we're trying to find the limit of at point c. We're going to call that function g of x. Okay, so g of x at point c is in between h of x and f of x. So here's what the squeeze theorem says. So let's say, well, first of all, we have to make a statement. We have to say that f of x is less than or equal to g of x, which is less than or equal to h of x on an interval. That's the first thing that has to be true for the squeeze theorem to work. And you can see that for this interval right here around c, that is true. F of x is less than g of x, and h of x is more than g of x. So that's the first thing that has to be true. So now let's say the limit as x approaches c of f of x, I don't know, let's call this number L, right? Whatever it is, it's approaching L. So the value of the limit as x approaches c of f of x is L, right? Okay. And the limit as x approaches c of h of x is also L. Then we can make a statement now of g of x. Therefore, at x equals c, the limit as x approaches c of g of x must also equal L. So hopefully that kind of makes some sense, right? If the value of the limit for the function above it is L and the value of the limit of the function below it is L, then we can assume that the function that's squeezed between both of those is also L, right? And I left some space here, but really these would be all touching so that they're exactly at L. So let's use this in practice. So example 1 says, if f is a continuous function such that f of x is greater than k of x but less than m of x, explain why the squeeze theorem cannot be used to find the limit as x approaches -1 of f of x. Okay, so let's figure that out. First of all, let's find the limit as x approaches -1 of k of x. So of k of x, that's going to be -x squared minus 2x plus 3. So let's find the limit of that. So we can just use algebraic substitution here. So let's go ahead and plug in -1. So that's going to be, do my arrow, -1, it's negative, right? -1 squared minus 2 times -1 plus 3, which becomes, that's positive, and then we have a negative out here, -1 plus 2 plus 3, that whole thing equals 4. Okay, so the limit of k of x is 4, right? The limit of k of x is 4. Now let's do the limit as x approaches -1 of m of x, and I'm just going to write this out here, 1/2 x squared plus x plus 13 over 2. Now let's plug in -1, 1/2 times -1 squared plus -1 plus 13 over 2. Now I just get to do some number crunching. This becomes 1/2 minus 1 plus 13 over 2. 13 over 2 plus another half, that's 14 over 2. That's 7. 7 minus 1 is 6. So the value of this function is 6. So right away, when I evaluated this function at negative 1, I got 4. When I evaluated the second function at negative 1, I got 6. So they're not equal, right? So since, and that's also, so 6 and 4. So it is still true, right? Because 4 is less than f of x, which is less than 6. So the value of f of x is somewhere between 4 and 6. But we can't use it to say exactly what the function is. So what we're going to say to prove that it cannot be used is since the limit as x approaches negative 1 of k of x does not equal the limit as x approaches negative 1 of m of x, the squeeze, I always spell theorem wrong, theorem cannot be used. These would have to be the same value to use the squeeze theorem. So that's an example of when it cannot be used. All right, let's do another one. Suppose there is a function g of x that it is in between f of x and h of x when x is near negative 1 again. So there's the function for f of x, there's the function for h of x, and it's telling us to find the value of the limit at x equals negative 1 for g of x. When you see this sort of setup like this, you know on a multiple choice question or on the AP exam, they're going to want you to use squeeze theorem. Okay, so let's do exactly what we did for the last one. First, let's find the limit as x approaches negative 1 of, let's do f of x first. So negative 1/4 x squared minus 1/2 x, which becomes negative 1/4 times negative 1 squared minus 1/2 times negative 1. This becomes negative 1/4. This becomes plus 1/2. And when we solve that, we should get 1/4. Okay, so the value of this function, the value of this limit of f of x at negative 1 is 1/4. Still trying to figure out why this iPad gets blurry on me when I'm writing. Okay, limit, now let's do the other one. As x approaches negative 1, let's do h of x, of 1/3 x squared plus 2/3 x plus 2/3. All right, now let's just plug in negative 1. Which becomes, this is still 1/3. This is minus 2/3. This is plus 2/3. These two cancel out, and I'm left with a positive 1/3. So right away, I'm checking. Does the limit of f of x at x equals negative 1 equal the limit of h of x at x equals negative 1? And they do not, right? One's 1/4 and one's 1/3. So the limit as x approaches negative 1 of g of x cannot be determined since the limit as x approaches negative 1 of f of x does not equal the limit as x approaches negative 1 of h of x. Essentially, the squeeze theorem cannot be applied, right? Kind of like exactly in the last example. Except here I just changed my answer to match what it was asking. All right, one more example. Use the squeeze theorem to find the limit as x approaches c of f of x. And they just tell us f of x is in between these two functions. Let me just box that in. It says f of x is between these two functions and that c is 0. All right, so let's figure it out. Let's find the limit as x approaches c is 0 of 4 minus x squared. Let's do this side first. Okay, now I can just plug in 0, which is 4. Now let's take the limit of the function that was bounding it from above. X approaches 0 because c is 0, and then I'm just plugging in 4 plus x squared. That becomes 4 plus 0 squared, which is 4. So here's our first example where the limit of the function, the lower bound function, and the limit of the upper bound function are equal to each other. Therefore, they are equal to each other. So we can use the squeeze theorem to prove that the limit of f of x at x approaches c is also 4. So since, this is how you'd write this whole explanation. And I would, since 4 minus x squared is less than f of x, which is less than 4 plus x squared, and the limit as x approaches c of 4 minus x squared equals the limit as x approaches c of 4 plus x squared, then, and I might also put here, equals 4, right? The limit, this thing keeps getting blurry on me. So it says, since 4 minus x squared is less than or equal to f of x, less than or equal to 4 plus x squared, and the limit as x approaches c of the function, that's the first function, equals the limit as x approaches c of the upper bound function equals 4, then the limit as x approaches c of f of x equals 4 as guaranteed by the squeeze theorem. So that would be how you answer that question, right? You have to state all of the things that are required for the squeeze theorem. 1, that f of x is between those functions. 2, that these functions are, when you take the limit as at the point x equals c, they are equal to each other, and then that value is 4. Then I can now say that the limit of the middle function here, f of x, is 4 because that's guaranteed by the squeeze theorem. Okay? All right, this question I want you to try on your own. So write it down, pause, and then what you're going to do when you are done is I posted the solution on Google Classroom so you can check your work and see if you're understanding the squeeze theorem. All right? Until next time.